Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you all for coming. Want to introduce George Dravosky. I can always mispronounce it. George is coming to us from Caltech and the Center of Advanced Computing Research. So George has a really great background, obviously, in this space, but also one of the things we've been working with George on is looking at, how can we bring things like Worldwide Telescope and other technologies to bear in some of the astronomical spaces. So introduce George to you. Thank you.
Thank you very much, Dan. Thank you for arranging this. Pleasure to be here, of course. And so to satisfy the curiosity, Machina Coelestis, the celestial machine, was title of the book by Johannes Hevelius, a famous astronomer. And there was a telescope that he built, a machine for the heavens. Now, it's different kind of machines that we use to study heavens, so I couldn't resist. Before I begin, I felt that here at Microsoft I have to pay homage to the great man, Jim Gray, who really did help us so much and who certainly deserves a lot of credit for effective things that are happening in virtual astronomy and digital sky surveys. So we'll try to make him proud of what we're going to accomplish on the basis of what he has started. And here are some of my principal collaborators whose work I'll be describing. So what I will do today, I'll first cover some of the general background facts about how astronomy is being completely transformed by information technology and computation, exponential data avalanche, mention virtual observatory as a framework. I will then talk about a particular digital sky survey that we're now completing at Palomar, and a successor survey is already planned. And that is a good precursor and testbed for bigger and better things to come, including Large Synoptic Survey Telescope. I'll tell you about some of the scientific excitement that's driving this work about astrophysics in time domain, which I think is becoming one of the very active and exciting areas and will probably dominate LSST science. And some of the computational infrastructure that we have built to deal with this now. And at the end, I will conclude with ideas for possible projects that would love to develop some collaborations or further the existing collaborations, which I think would be of interest to you, perhaps, and certainly be very useful to us. So as you probably know, astronomy today is dominated by large digital sky surveys. Sloan's survey being very famous, many surveys at Palomar and so on. These surveys typically gather several tens of terabytes of image information and detect of the order of billion sources, stars, galaxies, whatnot, and measure hundreds of attributes for each source. And they operate in all wavelengths, from radio to gamma rays, mostly optical and infrared though. They support very broad range of science, and that's a very important thing. The information content of these data sets is so huge that it can satisfy scientific needs way beyond what survey originators have had in mind. They may do 1% of all science available. There's just so much useful information in them. And that spans a broad range from statistical studies like large-scale structure, discovering unusual things, quasars, or whatever. Surveys are now being federated in the virtual observatory framework. I'll say a few words about it. And we're now in an interesting transition. You can think of sky surveys as large panoramic digital photography of the sky. You just do it, it's beautiful, like in Worldwide Telescope. But what we're going to now is digital cinematography of the sky, where sky will be covered many, many times repeatedly to a great depth. And we will look for things that change and move. And the information jump will be just like from staring at a still picture to watching a full movie. So this is where a lot of new exciting challenges will come, as well as a lot of science, going into petascale data sets and so on. the amount of information in astronomy doubles every year and a half, just like I think every other field, just like Moore's law, for the same reason, the same technology drives them. And this is a plot that my friend Alex Zalé has made. So astronomy today has roughly between 1 and 2 petabytes of data in archives. And we generate data at several terabytes per day rate. And of course, the rate grows exponentially too. But it's not just the volume, it's the complexity of the data. The large number of attributes measured and things that you get by combining of different scales and different wavelengths and so on. And so just a couple pictures to illustrate that. Here is composite of Crab Nebula in X-rays and visible light. And in visible light, you wouldn't have possibly guessed that there is a structure. So any given data set is biased and limited in its own way, and you'll be misled unless you combine the data. So we study complex phenomena like star formation, galaxy formation, and so on. Not any one given channel of information is sufficient, and to study complex phenomena, you need complex data too. But there are a lot of challenges in that. So where we're heading is the things like Large Synoptic Survey Telescope that both Gates and Shimoni had expressed interest in a tangible fashion. This project is supposed to come to completion in about 6 or 8 years from now. It will be a 8-meter class telescope, will generate of the order of 20 terabytes of data per night. It will create petascale data sets, a camera with 3.2 billion pixels. It will cover large chunks of the sky repeatedly with different cadences and so on. You can think of it as sort of doing full-blown Sloan digital sky survey per night, every night. So to pull back a little bit, I mean, these are examples in astronomy from what I think is a much broader picture that we see all over the science, that we have first collecting a great deal of data from telescopes or biological sensors or oceanographical sensors and so on. Then we need to do something civilized with the data, put them somewhere, index them, and so on. And we know pretty well how to do all this. Right? So virtual observatory so far has been really a data grid. Then comes the interesting part of extracting knowledge from bits, which is, of course, what science is all about. Data are purely incidental to our mission. We're in knowledge business, not the data business. And this is where we have a lot of exciting technical challenges today because of scalability of data mining algorithms and optimal access to the structures and data and so on. Visualization is a huge, huge issue because we're dealing with hundreds or thousands of dimensions of parameter spaces, and of course biologically we're limited to 3D vision. So this is of course where real human input is needed. So these are the technologies that I think are now a key bottleneck, and of course feedback steps in every part of this loop. So
database technologies span also data mining.
Yes, this is way oversimplifying, but it's just to show that there is a flow from you get the data, have to keep them in some good way, then you have to extract knowledge from them, and of course there is feedback all over this diagram. Right? You're quite right. And I thought about this, and why is this not the same old stuff just with more data? And I came up with 2 fundamental reasons why science is different in the era of exponential abundance. The first one is that we'll never be able to actually look at all the data. That humans can perhaps examine of the order of terabyte per year, give or take, depending whether it's pictures or text. But for the first time ever, we won't be able to actually look at all of our measurements. So you have to have good technologies to assure that you got good stuff. And more interestingly, the data are so complex with such an information content that there is knowledge present in there that simply cannot be comprehended directly by looking at it because of dimensionality, if no other reason. And so we need sophisticated new knowledge extraction technologies to help us get the real understanding from the bits. So all this amounts to really a growth of a new scientific methodology for science with massive and complex data sets, which is common to all different sciences. And yet, even though we have this amazing wealth of information now, we're not doing very well in extracting knowledge from it, and that's because scientists are not well equipped to do it. And that operates in several different ways. First, we don't have tools. And second, we don't have the expertise. These are not the things that I have learned in grad school, and I'm not, well, I am actually, but most professors are not teaching them to their students because they don't know them. And that's where Jan's program really comes in. So education is hard work, and we'll have to work on it, but we do need tools. And one theme that we've been trying to develop at Caltech is what would it mean to create a new generation of scientific data analysis systems that are not parochial and peculiar to a particular project or experiment? In the same sense that you have a statistics package that you can use for anything, biology, physics, geology, health, whatever, why don't we have next level of sophistication for data analysis, massive complex data sets that can grasp the mathematical universalities that are seen everywhere and enable scientists to do their job with massive and complex data sets. The way I think of it in a sense is like everybody's got Microsoft Office on their desktop or laptop, uses PowerPoint, Word, Excel, whatever. Why can't we have data mining, data exploration equivalent of Microsoft Office, that every scientist would use every day? I mean, we have these terabytes and petabytes coming and raining on us, and we're not doing much with them. Why isn't every scientist in the world doing data mining all day long? And the reason is we don't have tools, and we don't know how to do it. So we're trying to do something about that. Okay, back to astronomy. This enabling exponential avalanche of data and computational power poses a challenge. We have to be responsible in actually extracting knowledge out of it, and this is where virtual observatory concept came from. It was really to create a full-blown open research environment for astronomy in the 21st century, unifying not just the data resources, but compute and analysis resources. So essentially, users would go to one-stop shopping into this environment and do all of their work there. And this is a new kind of scientific research environment. It's very much web-centric and distributed, and it's replicated now in many different fields. So that has been going on for the past 8 years or so. And indeed, virtual observatories are real. There is US effort, and there is European effort, and there are all these different national efforts, and they all talk together in International Virtual Observatory Alliance. So I'm just showing this to demonstrate that the astronomical community at some level has gotten its act together and is really trying to combine its expertise and resources in standardization in some good way. Let me now talk about this particular sky survey that we're doing, because I think it represents a fairly good illustration of where the things are going. A Palomar Quest survey, Quest is an acronym, actually stands for Quasar Equatorial Survey Team, uses this telescope at Mount Palomar, 48-inch, which is where all the historical famous sky surveys were done in the past, and now uses this camera with 112 CCDs, had 160 million pixels. For a short period of time, this was the biggest astronomical camera in usage. Professor Charlie Bolte at Yale and myself are co-PIs, and we have large network of collaborators worldwide in the US, in Switzerland, in Mexico, and whatever. So what we do is we scan the sky, we park telescope and the sky drifts by, we'll read out the detectors, and we just cover it again and again, roughly twice the area of Sloan survey, and typically get about 70 gigabytes per night. And we have altogether, I would say, about 60, maybe almost 70 terabytes of data, which is about twice the amount that Sloan has gathered. The reason we can do this is, of course, that we can build on the work that they and us have done before. So there are several pipelines that are optimized for different science goals. I will not talk about them except for one of them. And we built in all of virtual observatory standards and formats and everything from the beginning. This was the first major sky survey completely built in virtual observatory era. So there are many different scientific things we're trying to do, but the most important one is what we call exploration of the time domain, and I'll spend some time talking about that. But one thing you can do is you can think of this as a little baby precursor to serious digital synoptic sky surveys that will come, like Large Synoptic Survey Telescope. We collect less than 0.1 terabyte per night. They will collect 20 terabytes per night. But there are some very similar methodologies and problems that need to be addressed. I'll mention that we've done this piece of public outreach, which is this big picture, cleverly named, in Griffith Observatory. It's 20 feet high by 152 feet long. That Jonathan just flattered me that he liked it so much. And this is human figure somewhere here, shown to scale. And it's a SWAT through Virgo cluster, and if you walk by it, it's like if you're on a promenade deck of Starship Enterprise. And now this cylinder in the sky is being incorporated in Worldwide Telescope. I can't wait to see it. But this is the largest astronomical picture ever made physically, and it's reproduced in porcelain. Steel plates and porcelains will last for centuries. And that was scary. When everything else we've done is gone and forgotten, this will still be there. So the science. All kinds of stuff that we're doing. We're looking for very distant quasars. These are outliers in some parameter spaces. There's a spectrum of one. We're looking for gravitational lenses and supernovae. This is picture. Another one is subtracted to, you see extra star. Those are used for standard candles for cosmology to measure the dark energy and so on. So, but the main focus now is what we call exploration of time domain. So let me talk about that a little bit. Usually, in astronomy, people think things don't change very fast, right? So, but they do, right? And you can think of it in two different ways. First, things that move, like planets, asteroids, stars move, wait long enough, you can see that. Or things can vary in brightness. They can vary because they really are physically varying some way, or because something happened to the light between you and the source, like lensing, something passed by, and so on. And without going through any detail, there are many different interesting physical processes that cause variations, ranging from catastrophic explosions in relativistic physics to simple geometrical changes and pulsations and evolution and whatnot. And the key part is that the only way you can actually understand these processes is through time domain. A single picture of a supernova will tell you exactly nothing other than it happened. You have to monitor its change and see what happens in order to get the physics to use it to understand what's going on. And in fact, we know about changes from milliseconds with pulsars to Hubble time, the evolution of stars and galaxies. So this time axis, which is relatively poorly explored, contains amazing amount of crucial information to understand physics and evolution of constituents of the universe. So how do we go about this in gathering the data? Well, these synoptic panoramic surveys will discover things that happen, that change. But then you have to follow up and get more information on those interesting things that happen. So you need to enable both of those. Thanks. Well, first, the things that move. Within the solar system, of course, there are planets and what have you. My colleague Mike Brown made name for himself by discovering dwarf planets and demoting Pluto. And here is one of them, the first one, Qual R. See how it moves, right? But the more interesting part is looking for something that might do this. Now, this one's pretty nasty, but here is a real picture from Siberia. This was a relatively small impactor, and yet it caused the equivalent of a 10 megaton airburst. And if it had it happen over inhabited parts of Europe, you could have, imagined. But
When did this happen?
1910, something like that. Events like this happen on planet Earth every few centuries. Events like, maybe not this big, but sort of like that every few tens of millions of years. And that's what did dinosaurs in. So looking for potentially hazardous planet-crossing asteroids may be, in fact, the single most important scientific experiment on this planet. And people who work for Pan-STARRS survey and LSST have this very much on their minds. And in fact, JPL group is using data from our own survey telescope to do this. So I think this is something that's extremely important to do. Okay, so outside solar systems, there is all manner of things that go bang in the night. Here is a little star that just goes boom. And what you see here is equivalent of solar flares, only much, much, much bigger. Sometimes they're black holes or neutron stars that suck material from nearby big star and falls in and loses, converts its potential energy into radiation. Explosions like crab or gamma ray bursts. Sometimes object passes between you and background star and magnifies it for a period of time. Here is the center of our Milky Way galaxy. There is a little black hole, 3 million solar masses in there. Occasionally, it gobbles up something and flares up. There is all kinds of exciting physics that goes on in time domain. So we see some of those. Here are examples of so-called cataclysmic variables. That is this kind of thing. The accretion doesn't proceed smoothly. Stuff falls in blobs, and when a lot of stuff falls in, you get a big flare. In my introductory astronomy class, I always have a homework problem for my students that involves computing energy dissipation if you drop a professor from safe distance to a neutron star, and something like a thermonuclear war worth of energy or something. So here are some of those in real life. See, fainter, brighter, they flare up. They get these exciting spectra with a lot of emission lines of ionized gas, hydrogen, helium mainly, and so on. And there are people who really care about this kind of stuff. We don't in particular, but those are still useful. Now here is an interesting historical vignette. Quasars, as you probably know, were discovered in 1960s as radio astronomy came of age. People found out that these funky blue stars are actually radio sources, and they got spectra and figured out, wow, a new phenomenon of nature, supermassive black holes and whatnot. In fact, quasars were spotted but not recognized as a new phenomenon as early as 19th century. There's a historical light curve from Harvard Plate Collection of one of the famous ones. And there are these, and they vary, and they're given names like variable stars. And everybody thought they're just some kind of stars, but in fact they weren't. So quasars were first seen as variable sources, most famous being B.L. Lacerti, giving a name to a whole class of variable quasars called blazars. Blazars because B.L. Lacerti quasar. We could have also called them quarks, but that didn't sound so good, so now they're called blazars. So blazar is a quasar with a jet pointing right at you. Now, you probably have seen some illustrations of that. The idea is there is a big black hole, there is accretion disk, stuff falls in, there's probably a magnetic field that's been threaded through the disk in a black hole, pinched very tight to very strong field strengths, accelerates plasma to relativistic speeds. The whole thing is like a giant accelerator in the sky. And if you see it from the sides, it's got beautiful radio jets and lobes. But if it's looking right at you, it's like an accelerator and you are in its beam. Fortunately, it's far away. And smallest variations get greatly boosted by relativistic beaming. And that correspond to changes. So here, it flare up and down, up and down. Here is a picture from our survey. Now you see it. Now it's kind of gone. This is one of so-called Cherenkov telescopes, which look for very high energy gamma rays and cosmic rays that come to Earth's atmosphere. Earth's atmosphere is used as a calorimeter. Particle moves faster than the speed of light in air, and it emits so-called Cherenkov radiation, which is an electromagnetic equivalent of a sonic boom. And so you can tell individual photons coming, and then you image them, and here it is. So this told us that there are plasma blobs in these objects moving towards us with so-called Lorentz gamma, which is relativistic measure of several hundred. Now here is a very exciting part of this. This probably explains the origin of highest energy cosmic rays. What's shown here is the spectrum of energies of cosmic rays, which has been flattened by being multiplied by the cube of the energy. Really, it's like a power law, but to make it easier to see, they multiplied, right? And at lower energies, we kind of know where it comes from, supernovae, pulsars, that kind of stuff. The origin of the highest energy cosmic rays has been something of a mystery. And now we're pretty sure it comes out of these blazars that are beamed towards us because there is a new result from a giant cosmic ray telescope in Argentina called Auger that has statistically associated arrivals of highest energy particles with directions to nearby active galactic nuclei. Here is the real kicker. This goes out to 10 to the 21 electron volts. This is 8 orders of magnitude higher than what Large Hadron Collider in Geneva will achieve. Now, in accelerator world, if you go up by a factor of 3 in energy, you're doing fantastic. Well, I can tell it's going to be a long, long time before we have an accelerator that's 100 million times powerful than Large Hadron Collider. In fact, never, right? So I'm sure that this is the future of experimental particle physics. Mother Nature makes these particles, and we don't have a clue what these particles are, right? But they're there. There aren't very many of them, but blazars make them and send them our way. So this would be a very interesting thing to nail down.
Do you think we'll be able to have enough data captured to data mine this and find this particle?
In due time. I mean, they're rare, but you know, see this is from like a couple experiments. You can tell the error bars, right? There's only very few, but they're there. They do exist. Okay, you don't have to go 100 million times more LHC. I mean, particle physicists will be thrilled to go this far, okay? This will be fantastic. But so, you know, here is cartoon is a black hole. There is all manner of exciting physics, so-called hadron cascades. I'm not going to go into that. And so, you know, that's telling us about many different things, including structure and evolution of quasars and what causes the cosmic gamma ray background and so on. The physics of these jets, which is very interesting in itself. The future of particle physics. And here is a really cute one that has come out recently. That we can use these cosmic accelerators to tell us about history of star formation in the universe. And this is how this works. We have these super high energy photons traveling through intergalactic space, which is also filled by starlight from galaxies. Now, 2 photons can do pair production. You know how if you annihilate electron-positron, you get 2 photons. The opposite can also happen in some circumstances. So, you know, you think starlight photon, who cares? But in the frame of center of energy frame of 2 photons, both of them are really high energy gamma ray photons. And a starlight photon and one of these super high energy ones together can create electron-positron pairs. So a starlight filling up space between galaxies acts as a fog. You don't think of it as starlight as opaque gas, but it is to high energy photons. It's the weirdest thing, right? And so it eats all the high energy photons, and if you put a quasar at redshift half, all this stuff is gone. Put it at redshift of 2, all that stuff is gone. So if you have a large ensemble of these, you can solve simultaneously both for the intrinsic spectrum and for the amount of attenuation as a function of time. And thus, you can measure density of starlight as a function of cosmic time without recourse to anything else, which goes as a star formation rate. Now, what we do now is we do deep surveys of galaxies, measure the redshifts, figure out how much stars are they making. We come up with these plots of history of cosmic star formation. And some of it is obscured by dust and some is not, and you don't know what you're missing because you're always missing some faint stuff and so on. This way, you couldn't care less. You measure completely independently what the history of cosmic starlight production was. So I think this would be a very, very good experiment to do. So these blazars are sources of cosmic gamma rays. This is an old picture of gamma ray sky from Compton Gamma Ray Observatory. You can see there are some sources. In fact, there are about 300 of them. And this is the whole sky, so the accuracy of these is like a few degrees. A new satellite is about to be launched called GLAST for Gamma Ray Large Area Space Telescope. And this is a simulated sky that will see thousands of these. You'll see them come and go. But to really nail down what's happening, you want to kind of capture them also in visible light and radio and so on. And this is where we can help. So we're now been talking to GLAST people how to merge our data streams, because they would be looking for flares in their own data. But they'll have some threshold, right? Let's say 3 sigma, right? I have something flare at 2.99 sigma, too bad, right? On the other hand, if there is an optical flare in the same circle at the same time, or close to it, then suddenly that 2.99 sigma source is 10 sigma source, right? Because of the joint probability. And so joining optical panoramic sky survey with these gamma ray surveys is going to greatly boost scientific returns for them. So we've been looking for more blazars. We first look at the known ones. You see them come and go. And now we've been devising algorithms to pick them out, or data, on the basis of variability alone, variability of color, without recourse to the traditional things like radio waves and so on, and to understand, do we really know that population? Because we want to use it both for that starlight experiment, for all kinds of other things. And someday, this will be the population of cosmic accelerators that people will be monitoring to do particle physics. So we're just kind of laying the groundwork for that. And we do find some. We just look for things that are variable, and see this one? They have continuum sources. They're like synchrotron light bulbs. There are no emission lines. It's just beautiful continuum light. And sometimes you see these big emission lines that are typical of quasars flaring up and down. So we have demonstrated that we can indeed find previously unknown quasars and blazars from variability alone using this synoptic survey. Now the next step is to join it with gamma ray data stream once that comes online in a few months from now.
Do you think that this type of signal represents a signature
Yeah.
that can be encoded to really look for signal patterns?
Well, getting spectra requires big telescope and it's expensive. Pictures are much cheaper. And so what we're trying to do is find statistical patterns of variability, or other spectral variability, to distinguish them from other things that vary in the sky, and also use other subsidiary information like color, which is kind of broadband spectral energy distribution. I'll come back to the question of event classification in a few minutes. This is a very important question. Well, there are also mysteries out there. Here's some from older sky surveys. I love this one. Here's a star which, because it was in plate overlaps, was photographed 6 times in all digital Palomar Observatory sky survey. And one night it did this, and it came back. And it's a normal star, a little hotter than our sun, not one of those cataclysmic variables and all that. And we don't have a clue why it did this, because we only found it years later in the archives. Now, most normal stars don't do this, right? 300 times brighter than normal. If our sun did it, bad news, okay? And we know that sun hasn't done it since the oceans were formed on planet Earth, because if it did it, oceans will be gone, right? And I always say, we'll put global warming in a whole new context, right? Yeah. Or, oops, so we've seen in archival material things like this. They look like a star. Asteroids usually move, so they smear out. They're there once, and then they aren't there again. And we went and took pictures of those same spots later, deeper, and in some cases we could barely see something faint, and most other cases we just couldn't tell. And we then even saw this in our news survey, things that come and go. These are same thing in 2 different filters, separated by a few weeks' time, I think. And we don't know what it was, because by the time we got to it, it was gone. So what we really want to do is catch them while they're hot. Find out in real time that something's going on. And so that's what we spend a great deal of effort of doing. And we develop what we call Palomar Quest Event Factory. So we scan the sky. We scan it actually same strip twice per night. And in each of those, we find a couple of million sources. We compare what's there tonight with what was there before. We'll look for things that are new. We usually find of the order of 1,000 possible things. We toss out some artifacts, do all kinds of software filters that go on. We end up usually with several hundred real things. And almost all of them are asteroids that are not moving very fast. There is a lot of rocks out there. And in fact, there is only a handful of things outside solar systems. So the asteroids outnumber astrophysical transients, and this is slow asteroids, not all asteroids, just slow ones that you can't see move very fast, by a factor of 100 or 1,000, depending where you are in the sky. So we think of asteroids as a vermin of the sky, because we have to get rid of them before we... And so sometimes they move nice and fast, zipping along. Sometimes they do weird things. Here's an asteroid. Here's some innocent star. Asteroid overlaps the star. You can tell asteroid's moving, but the star didn't move, so suddenly you think this star has flared up. Here's another one. Cover this pathetic thing. And you'd be amazed how often this happens, because there are just so many rocks flying around and there's a lot of background stars. So we're trying to do, mitigation and find populate databases and so on. The dismal thing is that to the depth of our survey, which is not very deep compared to say what Large Synoptic Survey will do, only about half of these asteroids are actually known, cataloged. And people who mine these things don't take them seriously because they don't go for one-night stands. They want you to do multiple observations, compute the orbit, and what have you. So now I'm trying to figure out who all has all these databases of one-night stand asteroids, get them all together, and do one gigantic computation to try to connect the dots with Keplerian orbits and repopulate the database. Because this is going to be a real issue for pan-stars, for LSST, for all other surveys. And these things outnumber real transients by a factor of 100 or 1,000, because of course there are also a lot more small ones than there are big ones. And some fraction of those are potential Earth impactors. And you really would like to know about them before they hit, like a few centuries before they hit, so you can mount planetary defense. If you see one that's going to hit in 3 days, then you just go and get drunk. But but if like in the year 2317, this one's going to hit, then you can actually do something about it. So.
When you have these two photographs of the same part of the sky, how much time is there between them?
Well, it varies. Okay, typically, well, what we do is we actually have them separated by a few minutes because of 4 rows of CCDs, but then we come back a few hours later, and by then usually they move far enough. I would say at minimum you want an hour apart in order to really tell. There's a lot of strange orbit because of differential motions in the solar system. Depending where you're looking at, things may look stationary, but then you wait a little bit and they zip off somewhere else. This is a huge problem. Most people who came into this field were simply unaware of. Well, of course, in retrospect, it was obvious, but it's one of those things.
The particular part of the sky that you're looking at that night.
Yeah, there are rocks all over. Mostly around the ecliptic, but they're also high up too.
How long does it take to do the whole sky, the whole northern sky? Say?
Depends. This is the survey strategies. Do you want to go deep? You often? How much? How many times you come back? And so a lot of thinking goes into planning cadences, because different cadences are optimized for different things. If you're looking for supernovae, you want to come back every few days. If you're looking for flaring stars, say, you want to be much more often, and that kind of thing. So there is a lot of scientific balancing that goes on into that. Okay, so pipeline worked. We started finding things that come and go. And in fact, some people actually used satellites to follow them up, looking for, gamma ray bursts that come out of optically detected things, which I thought was the first thing that ever happened. Usually satellites are a big, expensive thing, and they don't follow up things that happen, from ground-based observatories, but, they actually did. And then we got our act together and started getting spectra within an hour. And so here are examples of supernovae that we discovered in real time. And this is what spectra of supernovae look like. All these big bumps are actually emission and absorption lines that are Doppler broadened by explosion, which is up to thousands of kilometers per second. And these are young supernovae, which are useful for a variety of things. So they've been actually followed up by robotic telescopes that were connected to through so-called VO event net. I'll tell you about that in a second. And we see a lot of those cataclysmic variables. So this one's called dwarf nova. It's one of those things that you got a neutron star and a donor star, and occasionally, well, normally it's like this, sometimes it flares up. Here it is in Sloan's survey. So when we caught it, it was, 600 or 700 times brighter than normal with a spectrum like this. And do some follow-up pictures, still hot, and then poof, gone. Right? So there are a lot of things that when you look carefully in the sky that will do these things, and unless you get spectrum, you don't know what it was. And we find some quasars too, which were not previously known. That our real-time pipeline said, oh, there is something here now. It was not there before. We got spectrum. We found those were quasars or blazars. And it just illustrates how incomplete the catalogs are, because these two have never been picked up through radio or through any other way. And we just picked them up because they flared. Right? And so it's entirely possible that we have a very biased picture of what quasar population is like, because this is a new selection way. So, not having enough trouble with our own survey, we decided to collaborate with another one. There is a group in Arizona, and they are looking for killer asteroids with small telescope, 24-inch Schmidt on Catalina Mountain, or Mount Bigelow, and they just take pictures, several hundred square degrees per night. And they set 4 pictures separated by 10 minutes. And here you see a star that just flared out. So they're not interested about anything in outside solar systems, so we decided to collaborate. And they keep all the asteroids, and we look for things outside solar system. And sometimes we have rediscovery from Palomar Quest seen by Catalina. And so that's good, because you want to be assured that same thing can be found in 2 different ways, and so we understand our completeness and so on. And my favorite was, this is a famous merger galaxy called the Antennae. Beautiful space telescope pictures of it. And when galaxies merge, there's a lot of star formation. Here are these tidal streamers, and supernova went in one of those arms. Now, this turns out to be exactly the kind of supernova that are used for measurements of dark energy, so-called type 1a supernovae. And there are only like 20 of those in nearby enough galaxies historically that can be used to calibrate. So this was one of them, and we have Hubble Space Telescope proposal to actually connect the distance of the supernova with what we normally use, so-called Cepheids. Okay, so a little bit about infrastructure. So usually the scientific measurement process is you find things, okay, you think about them, you decide to get some more data, and that usually takes a year. But if the phenomenon you're studying takes minutes or hours, you darn well better do it at that short time scale. So we developed structure for this called VO Event Net, VO for Virtual Observatory. Roy Williams is the PI of it. And the idea is we suck in events from Palomar Quest Event Factory and now Catalina. We compare them to what was there before using virtual observatory archives. We publish everything immediately on the web. Somehow have to figure out what's interesting. We talk to robotic telescopes. In fact, there are no humans involved here. Our robots talk to their robots. their robots get some data sent back to our robots. Something exciting, then you go, wake up somebody and try to get a spectrum. And it automatically generates web pages with all the pictures. Now you see it, now you don't. There is a whole bunch of useful numbers and so on. And it's all posted, published on the web, and you can subscribe to it in any one of several different ways. And we're ingesting a number of different data streams and make them all public at once. Even have Google mashup for it someday, worldwide telescope mashup. And we link to all of the virtual observatory assets that are known on this part of the sky automatically. So still, in the end, a human has to look at this like, ooh, this is interesting or whatever. But it's at least been gathered together. So, at the end of all this, we discovered this is really hard work, right? That all interesting things are, outliers in some parameter space. It's there now, wasn't there before. It has unusual color and so on. But all problems with the data are also outliers in parameter space, which means you have to clean the data really well and not throw away the baby with the bathwater too. So there is contradicting demands of high completeness and low contamination. Keep all the good stuff and don't ring alarm too often. And we're kind of getting there. The other thing is that when we designed these software systems, we didn't think about real time. We're thinking, just like a sky survey, okay, there is a database, there is archive, we populate it every morning, blah, blah, blah. But in fact, if you're addressing it at the same time as you're taking the data because you're comparing with what you got before, then there are all manner of nasty little architectural conflicts that come up. And so we didn't think of that, right? So now we're trying to think about how would you design systems so there is a proper balance of dynamical and static data access and so on. And of course, we discovered that it's essential to have really good data to compare with, right? So we're doing something about all of these things. About the baseline comparison, we decided to develop what we call hypersky. And right now, what you do is usually have set of data, and you can render it as images or catalogs. But if you keep getting more and more and more data, if you're interested in time domain, then you don't necessarily want to have static thing. You just want to compute on demand. So you're scanning the sky. You want to compare just with that spot over there. And you want to have all of the previous imagery on all different wavelengths, all the different depths and so on, have flux histories. Was there something ever there before? Or is this really new and never seen before? And how deep? And what are the limits? Is there an X-ray source there? And so on. And you want to do this in some kind of smooth flowing way and also be able to do this in an archival sense. So we think of it as a completely dynamical way of panoramic sky representation that's computed on demand and driven by this massive data stream mining. So Roy Williams and Matthew Graham are also developing a concept what they call the event portfolios, which is how to capture and organize all the different information. Now, sky surveys are nice because the information is fairly uniform. It's always this kind of picture, right? But then you go to archives and pull something, and sometimes there is an observation and there isn't, and there is paper, and there is an email. Somebody said, oh, I think this is a cataclysmic variable. Somebody else says, no, it's not. It's this and that. And so somehow you want to capture all of that knowledge, information, and so on in a way that would make sense and be easily organized and retrieved for analysis or classification. And so they're thinking very hard how to deploy various semantic web technologies to do this. Then once you have all this information, you can feed it into analysis programs and classification. Classification of transients is a huge, huge big issue because you get a lot of them, but only few are really exciting and worth diverting resources to follow. And so the idea here is Well, we discovered something and we know very little about it. We know its brightness, maybe a couple different times. We know where it is. We know how fast it moves or doesn't move. Maybe we know something about shape. And that's just not enough. So then we bring contextual information from archives. What was there before? Is there an infrared source there? Is there a radio source there? Has anybody else seen anything like this? And that kind of stuff. And then we can try to classify it. There are two different ways in which you can do this. And so the one that we're really working on is Bayesian classification. That, for example, suppose you have supernovae, right, of different kinds. Well, a lot of supernovae have been observed by a lot of people, and so we have the light curves and so on. And so if you ask, if this were type 1a supernova, I have two brightness measurements separated by 1 day, and they differ by this much. What's the probability it comes from that distribution? On the other hand, if it's this other kind of variable, and so on. So you can, it's a very clean Bayesian problem. And then you can then figure out what's the probability of any given event being, say, supernova, this kind or that one, or quasar, or cataclysmic variable, or flaring star, or whatever, right? And these don't have to add up to unity, right? Then as you get new data, you revise these classifications. These are provided somehow to subscribers. Some people only want this kind of supernova because they only want standard candles to measure dark energy. Some people only care about flaring quasars because they're interested in gamma rays and whatever. And somebody wants to have something that has low probabilities all the way down the list. In other words, doesn't fit into any known category and could be a new and exciting phenomenon that nobody's seen before. Now, you want to do this automatically, robustly, in real time, without humans in the loop. This is a really difficult problem. And you can, of course, instantly think of other kinds of situations where you have similar challenge in security applications, in environmental monitoring, quality control, and so on. You have massive, messy data stream. You're looking for anomalies. You want to find out which ones you want to act upon. So we've been working a little bit on this with computer scientists at JPL. We came up with at least conceptual architecture that there are two ways in which we can approach this. There is a Bayesian approach and there is a machine learning approach. If we had a large collection of well-classified events and a lot of data, uniform data for many of them, magnitudes, colors, what have you, well, then in principle you can train neural net or support vector machine or whatever you like and classify them that way. But by and large, at least initially, we will not have that. You only have sparse information. Sometimes you have this measurement and sometimes you don't have that measurement. And so this is where Bayesian stuff is actually better. So for Bayesian, we'll try to classify, and then that'll feed learning algorithms. Eventually machine learning algorithms will come in. But somehow you have to prioritize follow-up and have automatic decision, like this is a really exciting one. Somebody please stop whatever they're doing and take some data on this object, kind of thing. And there are many, many interesting and difficult questions that come in here, as you can well imagine. Then comes this question of directed follow-up. All right, suppose you came up with all these probabilities. Now you can ask, ooh, I can't tell, is this a flaring quasar or a supernova? What kind of measurement will help me distinguish between these two hypotheses? Infrared magnitude. Is there a telescope with an infrared camera available to me now? Kind of thing. So that you can decide automatically, not you, computer will decide, to ask specific assets saying, could you please take such and such measurement? Now, our friends at JPL are interested in this because they're thinking in terms of spacecraft networks. Like you can have, say, rovers and orbiters in Mars, and a rover spots a dust storm or something and then wants an orbiter to take a picture. You don't want to go to Houston all the way back, have a supervisor decide and all this. So you want spacecraft network themselves to decide what data to take. And so this is a fairly interesting thing, that you can redirect follow-up assets. And again, you can think of in terms of other applications outside astronomy where this might be useful. Well, okay, so far this has been a baby play. So what we're getting today between us and other people is of the order of 0.1 terabyte per night. And we see, say, tens of transients, supernovae, flaring stars, what have you. Okay? What's coming up soon is things like Pan-STARRS and SkyMapper and all these various astronomical things. And they'll be covering of the order of terabyte per night and find about 10,000 per night. What's coming with Large Synoptic Survey Telescope is 20 terabytes a night, and they say between 10 to the 5 and 10 to the 6 transients per night. Now, of these, which 10 will you follow up photometrically, and which one you will take a spectrum of with your 30-meter telescope in Chile? And you better make the correct decisions, or else very soon you'll have no friends. This is going to be a huge problem, right? And we better solve it now when we have 2 orders of magnitude smaller problem, or 3, several orders of magnitude smaller problem, and as a hard problem as it is. Even if you had armies of graduate students staying up all night, you just can't do this with humans. This has to be completely automated and robust and reliable and scientifically validated. And we simply do not have technology or methodology that will let us do this. And of course, you can imagine, again, similar kind of situation in other massive data streams. And in fact, Alex Zalay was telling me about a problem that he became familiar with with military, collecting petabytes of data daily in Afghanistan to try to predict which roadside truck was actually a bomb that's going to explode. And they collect the data, they ship the disks to Germany. They have turnaround time of 2 weeks, by which time the damn bomb has exploded 2 weeks ago. This is an important thing, right? And clearly, we just don't know how to do this right. So this is a very challenging arena. So let me summarize what I told you about astronomy, and then I'll end up with one more slide. So I hope that I conveyed that this new time domain astronomy is something that's going to be very, very exciting. And it's actually a killer app of virtual observatory. It takes all of the virtual observatory technologies, distributed data, data fusion, all kinds of stuff, right? And now we have little surveys like Palomar Quest and going to LSST. And with larger data rates, data volumes, there'll be more science. And there is a remarkable range of interesting phenomena, from killer rocks in solar system to these ultra-relativistic cosmic accelerators pointing at you, and cosmic explosions of all different kinds and whatnot. And time domain is the way to find it. This, by the way, is Tycho Brahe looking at supernova, and everybody going, ooh, what's this? So aside from exciting science, there are obviously some very interesting technological challenges which can carry to other domains and can recognize any number of buzzwords. I'm sure you can add your own to this. And we need help, and we know it. We're not afraid to ask. So here I'll just end with this listed things that came up. I thought each of those can be a very exciting and interesting potential area of collaboration. First, what you may recall, I told you in the beginning, how can we bring effective, user-friendly, if you will, easy-to-learn data mining to every scientist's desktop or laptop? Sort of Microsoft Office for scientific analysis, if you will. But you also have facility class things. And there is the hypersky concept of making this dynamical pipeline / on-demand compute sky atlas in time domain system, which involves in workflows and all kinds of interesting architectural issues and so on. Then there is event portfolios, trying to use some of the semantic web technologies to collect and sort out heterogeneous data. There's a really difficult problem of real-time, robust event classification with sparse and heterogeneous data sets, and redirection of measurement process. And of course, there is computational science and education outreach, in which we have been already engaged through Jan and through Worldwide Telescope, and I hope to continue along those lines very much more. So I'll be delighted to talk to any one of you about any of these things, where I think those are exciting and pleasant problems, fun problems to work on. Thank you.
So what's your data management platform for all the work that you're doing right now?
Platforms, many. We do, of course, use SQL Server for some of the stuff. Yeah, we have too many different ones. Little databases of all kinds, MySQL here or there. As any scientific project, as opposed to engineering project, this simply mushroomed away. And we kept adding Band-Aids upon black boxes and so on. And then we said, oh, wish we have done it right, and so on. And so this is why we're now thinking for these next generation projects like Hypersky, like this desktop, laptop, data mining system. We got to do this in a civilized fashion and design architecturally things and define things in proper fashion up front. Because we're just dumb. We didn't know how to do it right. I mean, we had always an excellent plan. We only had 20 of them. As we kept changing, as our priorities kept changing, right? I mean, Jim Gray advised us wonderfully. I mean, we told him this is what we think our data problem is, and he said, do this, don't do that, and we tried, and then of course we changed our minds because, other things happen. So yes, we very much like to learn more how to do this properly next time.
Is that a potential
Yeah.
area of collaboration?
Yeah, absolutely, especially within the Hypersky concept, but also the data mining environment.
So another question is, I see a lot of parallels between your project and the Pan-STAR story.
Yes, absolutely. And theirs is going to be much more ambitious and powerful, and at least 1 or 2 orders of magnitude more data. As far as I understand, aside from looking for asteroids, which is their mandate from the Air Force, they do not really have working plans for proper time domain or real-time investigation. They have realized that they'll be drowning in data as is. And the dynamical stuff is a luxury, right? First they're thinking of their survey as sort of super Sloan, really. And then once they can control that, then they can perhaps get into a time domain. I'll be giving a colloquium at the Institute for Astrophysics in early June, and I'll be talking to them quite a bit about these things. Because we'll learn some things the hard way, and they can benefit from it. I would say by far the smartest thing that Pan-STAR's people have ever done was to get Alex Zalé involved and his group. But it's a huge, huge challenge. And just the stationary part, never mind the dynamical part.
Learning the concepts with something smaller and more manageable now will make it possible to make the right decisions in the design.
You'd hope so, yeah. I think Pan-STAR's people have been a little naive about the whole software scene for a while. Now I'm beginning to wake up. I mean, we all have been naive about this. It's the usual story. You just do not think how big deal the software is going to be. And I keep preaching this gospel, and people say, yeah. Everybody begins with, the software is something that students will write for free. Then the reality comes. I should tell you that, look, I've been in sky surveys business for a long time, and Alex and I co-founded Virtual Observatory Effort. You think I was not a fool, right? When we started Palomar Quest project, we had a full-blown, perfectly well-working pipeline. 2 years later, we began to actually get useful data with a completely different pipeline. So even if you think you know what you're doing, you don't know what you're doing because the real data is going to be different from whatever it is that you simulated. Right? Yes, Dinesh.
I was curious about the machine learning part of it.
The
machine learning.
Yeah.
So, I mean, often the best machine learning methods aren't scalable. So if you have lots of data, you basically go for the simplest possible methods like boosted naive Bayes or linear SVMs. So which ones are being used here?
Well, on event classification, we're still just poking around. We do a lot of machine learning classification for things like star-galaxy separation and for artifact removal. And there we use neural nets quite a bit just because my postdoc who knows that very well. He's got PhD in computer science on this. And so in the past we used decision trees. We've been experimenting with other stuff as well.
So generally, do you make the assumption that still at the moment that you can store all the training data in memory?
We don't have to. I mean, once you train one of those things, you just have a simple...
During the training process?
There isn't all that much data, right? But, I always have these, bad dreams and nagging feelings, we may be going about this in a completely wrong way, because things are not mathematically simple, there is noise, and it's not Gaussian noise, and there are glitches, and some things are numbers, and some other things are not numbers, there are flags, and right.
One of the things, the battling between computers being able to take care of the problems and solve, like you said, most of this data humans will never be able to look at. But there are still some problems that, like in supernova search, I'm familiar with friends with several people who are on the Puckett Steve, the supernova search team, that private teams have found more than anything else, and everything is blinked by humans. And
yeah, if you can get down to the data volume that matches the human bandwidth, sure.
Yeah. So part of the as the bandwidth grows, is there are still certain things where the computers will do what they do best to help filter things, to get them in a form ready and presentable to where humans can make final judgment in some case.
Right, and that's of course what we've always been doing. It's just that problems are getting much sharper and with a vastly greater scale. And you can get away with a lot of corner cutting when you just don't have very much data. And we're now getting in a regime that, well, we have to be real serious about this. It's a dirty secret, for example, in space measurements. There are a lot of data taken by spacecraft are never, ever looked at or examined in any way whatsoever. In fact, a lot of it was on magnetic tapes that are now unreadable. Hundreds of millions, billions of dollars were spent on all kinds of satellites and missions, and data were never used for anything. That was good old days, right? This was several e-folding times ago. We can't be doing that.
So in your talk, you talk about computational intensive astronomy.
Yeah.
And you refer to data mining as examples of such computations. What are the tools that you use to actually analyze the data? And I mean, is this part of queries? Is this post-processing? Is this on the fly?
All of it. I mean, it's usually we try to separate things. So there is a pipeline that's specific to the instrument or experiment, and goes from raw data stream into something that's calibrated. We think what it is, right? Then you analyze the output in different ways, And usually people have limited but well-defined question. So for example, Sloan, they would detect hundreds of millions of galaxies. Okay, I want to know how galaxies cluster, right? As long as I can separate stars from galaxies, there is an algorithm, letter it for a while, and out comes a little plot, x versus y, and there is a spectrum, right? But they're different ones, and they get better in time. But see, the thing is that kind of reduces the wealth of the available information to a simple-minded answer that you know you can get. And that worries me, because you're guaranteed to be losing some information because you're projecting that wealth into a particular, just one little, x versus y plot, right? And you're also defining the exact question. So there is such a wealth of information in these data sets that I think we should rejoice in the possibility of pure unconstrained exploration, looking for things we didn't know were there, right? As opposed to like, okay, I know I'm looking for quasars and this is the way to find them, and I'm going to, do this and that and draw a line in parameter space, and guys on this side are my quasars, right? That works, that's fine, you can do that, but who knows what else is hiding in there? So we've been experimenting with unsupervised classification, asking questions. Okay, machine, tell me how many different kinds of things are in my data, as opposed to only those that I think I know about. And I think that's just an infancy. And all these algorithms don't scale very well. I mean, off-the-shelf stuff will work fine on thousands of vectors in 5 dimensions. What if you have 1 billion vectors in 1,000 dimensions? You're just totally out of luck on this, right? Because things might scale as n log n in terms of numbers of vectors, but it goes dimension to some power. If you go Bayesian, then you're really up the proverbial, right? Like the dimension to second power, third power, whatever. So I think there is some need for some real research in scalability of data mining algorithms that will be well suited. Or we can just capitulate and say, we'll just have to live with approximate answers. And that's kind of grates against scientific mentality. But maybe that's the way to do it. So this is why I call this as a new scientific methodology. We're kind of trying to learn how to really work in this amazing abundance of information. Right? Yeah.
A question, do you know, earlier I had heard that part of the plans of the LSST to manage data volumes was to do some sort of comparison to a baseline and then extract only the differences and essentially throw the raw data away.
No, I don't think so.
Is there going to be an archive? Is it going to archive all the data that comes off?
I believe yes. They keep changing their story a bit, but I think what they're planning to is some kind of quick and dirty analysis in the base of the mountain for immediate reaction kind of stuff, and then schlep loads of tapes or disks or whatever every once in a while to US. Right.
Okay, so they are going to archive the raw data off, right?
Yeah, I actually don't know the details. I mean, I talked a little bit to those guys, but it's very much an ongoing thing. Right.
I mean, given that the tie-in was that when I first heard that, and I wasn't sure how accurate it was, but some of the people doing preliminary engineering on it, that was a plan of some in discussion, and I was concerned that what if you don't understand some of what you should be looking for, and then you throw data away, you could be.
Well, I mean, if you're limited to a depth of a single pass, then difference imaging is okay. But that means you will never achieve the depth that you could if you added up all the data, right? And to me, it would be criminal not to do that. Right?
Cool. Well, George, thanks again. This is great.
Thank you.
Appreciate it.
Yeah.
Thanks, everyone.